Hello, young people. Take a second. Appreciate the tan. Just got back from Cancun. Notice I still got the same shirt, same hat, same books behind me. Today we're going to talk about rigid body problems. Rigid body problems. Do you understand? We're going to take the forces, we're going to sum them up, set them equal to zero. We're going to take the torque, set them up, set them equal to zero. Right? And what's to follow? Some problems that are really going to knock your socks off. Hope you got some socks. Hate to see you lose your feet.
So here's our rigid body. It's comprised of a pinned beam of known mass. It has a hanging weight of known mass attached to the end. And there's a cable that comes in at right angles to the beam that's holding the beam up. The information we want to know, we'd like to know what the tension in the cable is. And we'd like to know what the forces are that are acting at the pin. Couple of things to start off with that are kind of important. We assume that at the pin there is a horizontal force acting and a vertical force acting, and we just call them H and V. As I said, the tension in this particular problem is coming off at right angles. You can see that because this line and this line are parallel. This line's acting as a transversal, which means this angle and this angle are the same angles. That means this is 65 and this is 25, and you add them up to get 90 degrees. This tension is coming off at 90 degrees to the beam. The weight of the beam is assumed to be acting at the center of mass, and its magnitude is m sub bg. We can deal with this hanging weight by simply assuming that there's a force equal to m sub hg acting straight down off of the end of the beam. So our free body diagram is going to look like this. We have tension coming off like so. We've got a couple of forces that are gravity related pulling down. We have horizontal and vertical force acting at the pin. So we're trying to figure out what the tension in the line is. And most people, just because they're familiar with Newton's laws in the translational version, might be inclined to want to sum up the forces in the x and the y direction and actually break things into component parts and do that, because that's what they're familiar with. But the best way to go about this is to actually sum up the torques about the pin. The reason why this is the smart thing to do is because you have these two unknown forces, H and V, acting at the pin. If you go summing up forces in the horizontal and in the vertical, you're going to have equations that are going to have components of T and H and V. You're going to have three unknowns. You're going to have two equations associated with what's happening in the x and the y direction, and you're going to need another equation which is going to have to come with summing up torques about some point along the beam. In other words, you're going to have to sum up the torques sooner or later, and you're going to have complicated equations because they're going to have three unknowns involved. If you sum up the torques about the pin just straight away, the torque due to H about the pin will be 0. The torque due to V about the pin will be 0, because forces acting through the point about which a torque is being taken produces no torque about that point. And what you will end up with will be a torque expression in which there is one unknown, T, the thing you're looking for, a couple of other torque quantities, and it will be a relatively easy expression to solve. And when you get done, you'll end up with what you want, which is an expression for what T is. So we're going to start out by using the rotational version of Newton's second law, which says that if you sum up the torques about any point at all, that will equal a mass-related term, which we'll talk about later, times the angular acceleration about that point. Writing it out for our situation, here we have the individual torques summed up, equaling that mass-related term I times the angular acceleration alpha. We've already figured out that the torque due to H and V are 0, and we can tell that because the body is in static equilibrium, the angular acceleration is going to be 0. So the next thing we need to do is to figure out how to do torque calculations. And in fact, there are actually three different ways you can do a torque calculation. I'm going to show you all three of them, and I'm going to do it on the torque generated by the gravitational force acting on the beam, which we're assuming is acting at the center of mass of the beam. Here I've shown a free body diagram minus all the forces except gravity just to make it easy to see what's going on. So it doesn't matter which of the approaches that you use. The first thing you're going to have to do is to define a position vector that is going to proceed from the point about which you take the torque. In this case, we're taking it about the pin, to where the force acts, which in this case is going to be the center of mass of the beam. That position vector is the R in the R cross F relationship that defines torque. In our problem, that position vector has a magnitude of half the length of the beam, L over 2. The first approach we're going to use I call the definition approach. And I call it that because basically it's just the execution of a cross product. In the execution of a cross product, you take the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between the line of the two vectors. The two vectors in our problem are gravity and R. The line of the force is like so. The line of the R vector is like so. Here is the angle between the line of those two vectors. So if we were to go ahead and write out this cross product evaluation fitted to our situation, the magnitude of R would be L over 2. The magnitude of F would be mg, and then times the sine of this angle. As a minor note, this angle right here is the same as the beam's angle, phi, plus 90 degrees. And you can see that because this angle and this angle are the same, and this additional bit here is 90 degrees. I've done that because the sine of that quantity is the same as the cosine of the beam's angle. And this bit of information is going to be important because when we do the calculation using the other approaches, we'd like to be able to see if they all come out to be the same value. And in fact, they are going to all come out to be this value, but we needed to get it into this form to be able to see that was true. The second approach is what I call the R perpendicular approach. Sometimes it's called the moment arm approach. And it basically takes the magnitude of the force times the component of R perpendicular to the force. This is the way that I would characterize it in an equation. Here is the perpendicular component of R. Here is the magnitude of the force. This approach tends to be the easiest one to use in most instances because there's a very simple question that you can ask that allows you to determine what R perpendicular is fairly easily. That question is, what is the shortest distance between the point about which you're taking the torque, in this case the pin, and the line of the force, in this case the line of mg. So it's asking what's the shortest distance between that point and that line. If you just think about it, you can see that this is going to be the shortest distance between that point and that line. And once you have that visualized, then you can use the geometry to figure out how big that length is. Here is the angle of the beam. This distance is L over 2. Here you have a right triangle of which this is one of the sides. It's the side adjacent to the angle you know. So R perpendicular is going to be L over 2 cosine of phi. Putting that into our torque calculation, R perpendicular, L over 2 cosine phi, magnitude of F, mg, we now have a relationship that looks just like the one that we just derived earlier using the definition approach. The third approach is what I call the F perpendicular approach. It takes the magnitude of R and multiplies it by the component of F perpendicular to R. And I would characterize it like so. Here is the magnitude of R, here is the component of F perpendicular to it. The easiest way to figure out what F perpendicular is to identify what F parallel is. In other words, what's the component of mg that's parallel to the line of R? And so there it is. Once you have that, you simply draw a perpendicular to that vector. Perpendicular to that vector is going to identify what F perpendicular is. And once you have that visualized, once again, you can use the geometry to figure out what that is in terms of mg and any angles you happen to know in the system. So if you do all of that, you come up with an expression for what F perpendicular is. You go back up over here, you take that and you put that in like so, you put the magnitude of R in like so, and once again we come up with the same expression for the torque that we came up with from the other two approaches. The last thing we have to do when you're doing a torque calculation is to figure out whether the torque is positive or negative. And without much discussion, I'm just going to tell you, if the force that you're looking at is tending to make the body want to rotate counterclockwise, it's a positive torque. If the force makes the body want to tend to rotate clockwise, it's a negative torque. So in our problem, gravity is acting like so. Relative to the pin, it's tending to make the system want to rotate clockwise, which means gravity is producing a negative torque. So I'm going to write out the torque as a vector minus the unit vector, negative, and then there's the magnitude. So in summary, here is the amount of torque that gravity is producing due to the weight of the beam. The torque that the hanging mass is generating is going to have very similar form. I mean, it basically parallels the force that gravity is producing. The only difference is that the r vector isn't going to L over 2, it's going all the way out to L, so this is L. And the subscript for the mass is m sub h, not m sub b. The tension, its r value is 3/4 L, so there that is. Its magnitude is T, and the angle between the line of R and the line of T is a 90-degree angle. So if we just use the definition here, we come up with this relationship. So now it's time to just sum up the torques and put them equal to I times alpha, which is 0. If you had a problem like this on a test, given the kinds of time constraints that tests impose, this would probably gain you most of the points. Here you're identifying generally what you're about to do. Here you're putting it fitted to the problem. Here you're actually putting in the parameters of the problem. By the time you get to this point, you've pretty much taken care of pretty much all the physics. If you had time and were expected to come out with a numerical value, you would probably do a little bit of algebra, put in the numbers, and come up with an expression for t. Okay, so that previous whole section seemed like it took a really long time, but in fact on a test, if you did it, effectively what you would do is you would show the forces and you'd sum up the torques about a particular point, and it would take you a couple of minutes to do. And when you got done, then you'd have to deal with H and V. And the way you would do that is by using Newton's second law in sort of a traditional way. You'd draw a standard free body diagram. You'd break T into horizontal and vertical components, just like you would do for a standard Newton's second law problem. You'd sum the forces up in the x direction, so here you've got a component of T in the x direction. It's negative because it's off in the negative direction. Here you've got H, it's positive. You'd put it equal to MA, which would go to 0. You'd put in numbers, there's your H value. Sum up the forces in the y direction. Another component of T, a couple of mg values, a v value, you put them all in with signs included, equal to MA, which goes to 0, put in the numbers, value for v. So that's it. That's a rigid body problem. You'll have to sum up the torques about some point. If you're clever, you'll pick a point that will allow you to eliminate some of the unknowns. At some point down the line, you'll probably have to sum up the forces just like in the old days. And everything gets put equal to 0. That's it.